I have 3 examples where I just want to integrate. And in these examples, I really just want to use the fundamental theorem of calculus part 2, the evaluation theorem. But one of the lessons we'll see over and over again is sometimes it's easier to do calculus if we do a little algebra first. So what I'm going to do on this first one is simplify the integrand. Because I think the top of this function factors. In fact, I think it factors into a t plus 2 and a t minus 1. And there's the nice part. Those t minus 1s cancel. And I'm left with an integral from 2 to 4 of just t plus 2. dt, of course. So let's see, I need an antiderivative, so 1/2 t squared plus 2t, evaluated from 2 to 4. All right, let's plug that 4 in. 4 squared 16 divided by 2 is 8 plus 8 more minus, now I have to plug a 2 in. 2 squared is 4 divided by 2 is 2 plus 4 more. So let's see, I have 16 minus 6 is 10. There's a nice happy final answer for number 1. So in number 2, I think I might be in that same place where I have to do just a little bit of arithmetic before I get started. This time I think some trigonometry might help us out. So I'm just going to start by trying to simplify the integrand. So I'm going to square this. I end up with a secant squared, and that's good because I know exactly how to integrate a secant squared. Plus 2 times secant tangent. Okay, well again, that's a antiderivative I know, plus tangent squared. All right, well, I don't know an antiderivative for tangent squared, but there's something else rolling around in my head. So I'm going to break out another board, write that integral we're working on down, and then see if I can do something with that tangent squared. So there's exactly what we had on the other board. Now we're just going to try to see if we can keep working on it. And so let's see, what else was in my head about that tangent squared? Well, I know there are relationships between my trigonometric functions. In particular, I'm thinking about my Pythagorean identities. So sine squared plus cosine squared is equal to 1. And if I divide every term by cosine squared, I end up with tangent squared x plus 1 is equal to secant squared. All right, well, if I take 1 away from both sides, I can write that tangent squared x as secant squared x minus 1. And just like here, I know how to find an antiderivative for secant. All right, so 0 to pi 6, I have that secant squared hanging out there. I have 2 secant tangent. And now instead of tangent squared, I'm going to write this down. So I realize I really have 2 of those, and that minus 1 I'll just throw in there at the end. And I'm ready to find an antiderivative. The antiderivative of secant squared is tangent, so I have 2 times tangent x there. The antiderivative of secant tangent is secant, so I have 2 times secant x. And then minus x, the antiderivative of 1, which I will need to evaluate from 0 to pi over 6. Well, the tangent of pi 6 is root 3 over 3. The secant of pi over 6, well, let's think about that. I actually have to think about a cosine first. The cosine of pi over 6 is root 3 over 2. So that's 2 times 2 over root 3 minus pi over 6. All right, now I need to plug in a 0. The tangent of 0 is 0. The secant of 0 is 1 times 2 is 2. All right, so I need to do some arithmetic here. Or really just rewriting things, and I have a minus 2. I could multiply top and bottom of that by root 3 and at least have a common denominator. And let's see, that would be 6 root 3 over 3, so just 2 root 3 minus pi over 6 minus 2. And there is an ugly answer, but it is our answer. All right, well, I've done the two problems that we saw originally, but I told you I had three I wanted to do. And so there's just one more, where I want to integrate from 1 to 8, in parentheses, x to the 1/3 plus 1 times the quantity 2 minus x to the 2/3 all over x to the 1/3. And again, I think what I'm really trying to drive home in this video is that sometimes it's easier to simplify in the integrand first. So I'm going to start by multiplying out what's on top. So I have 2x to the 1/3 minus x to the 1st plus 2, see, minus x to the 2/3 dx. No like terms hanging out there, and that x to the 1st, that looks weird, so I'll just write that as an x. Now I'm going to divide every term by that x to the 1/3. 2 minus x to the 2/3 plus 2x to the minus 1/3 minus x to the 1/3. Remembering we subtract exponents when we're dividing things with the same base. And what I now have is just a bunch of power functions to find antiderivatives of. So 2x minus, I need to add 1 to 2/3, so I get 5/3. So that'd be a 3/5 out front, x to the 5/3. All right, and again, add 1 to that, and I'd get a 2/3. So I get a 2/3 here. Flipped upside down, it'd be 3/2 times 2, which is just 3. Add 1 to the exponent, I get 4/3. And I need to evaluate that from 1 to 8. All right, so I plug an 8 in here, and I can think of that over 3 as a cube root, right? So the cube root of 8 is 2, and 2 to the 5th is 32. 32 times 3 is 96. So I have 96/5 there. Let's see, that's going to be a 12. And that will be a minus 12. So that's actually kind of nice. Minus, and now I got to plug a 1 in everywhere, and that's a little bit easier. All right, so now I need to simplify that. I'm going to turn to my trusty TI-84 for that. So I have 16 minus 96 over 5. All right, and the 12's cancel, so I have a minus 3.2 from that first bit, and that's minus 16/5. So I usually write that down here, but I've kind of run out of room, so I'm going to cheat and write it up here. So minus 16/5 minus, and now I need to simplify that set of parentheses, so 2 minus 3 over 5 plus 3 minus 3 over 4. 73 over 20. Oh, minus 16/5 minus 73 over 20. My final answer is minus 137 over 20. So there are 3 definite integrals where it really helped us out to simplify the integrands first.